So you must have gotten both your shots then, shall we? If you're able to
travel.
Oh,
my first shot was like January.
Yeah.
So they put it the same as, for some reason I don't understand, they put university people, the school teachers.
Right.
So we were out a while ago, and the kids are out as well. I mean, they're now. Our problem is convince the people who don't want to take the shot to take the shot.
Yeah. Yeah, there are all these lotteries now in all these states. Like, you should have waited to get shot, so you can enter the lottery.
Well, I don't want the other kind of lottery of getting it.
Well, that's true. Yeah.
So for the speakers, I guess the rule is 10 minutes. So I will just give you a private message at about 8 minutes to tell you have 2 minutes left. And then we'll wait for 30 seconds or something for people to type in their questions. And then Romeo will start go through the questions for about 3-4 minutes. Then we give people another minute or two to transition to the next talk.
Okay.
All right, it's time, right?
Yeah, I think so.
All right, so let's get started. Welcome to section 3A. So this is the Asian European friendly session of the conference. We'll have 5 talks, and we'll have first 3 talks all about related to this SQL30 project. First have Valentina give us overview of the SQR30. Go ahead, please.
Okay, thank you very much. And I'm very pleased to be here to present you this new project. First of all, a couple of slides of scientific motivation for the survey. So we all know that the quasars at redshift 6 are extremely important probes of the ionization epoch. And the first quasar in this redshift range were found in the Sloan Digital Sky survey. And here I show this famous plot from the review by Shawi, showing all the quasars that were known at the time. And the important result, one of the main results that was obtained from this sample was the evolution of the effective optical depth with redshift that was showing this upturn that you see here at redshift around 6 and increase also of the dispersion of the effective optical depth values that were interpreted as a signature of the end of the ionization process. In the last 5 years, we have that the number of quasars at redshift larger than 5.6 has increased by a factor of almost 5. And this was thanks to the availability of large area service both in the optical and in the near infrared. However, we had that at the same time, the number of good quality quasar spectra that were available was very small, of the order of 10 in 2018, and also very heterogeneous. So this is why we decided to propose to ESO this large program of about 250 hours of observation with the X-Shooter spectrograph that I remind you covered the redshift range between 300 nanometer and 2.5 micron. In order to create this sample of bright quasars, of course, we need to observe the bright objects to have a good quality spectrum, observe at intermediate resolution between 8,000 and 9,000 and a relatively high signal-to-noise ratio. Here, the observations are almost completed, and here you see a summary of the spectra nicely put together by Christine Eilers, who is part of the collaboration. The plus, let's say, of this sample is that we have also ALMA and NEWS parallel programs going on from the same objects, and that the reduced data will be released to the public as soon as the observation will be completed. So XUR30 is a quite large collaboration, including many of the people working on the subject in the world. We have people, of course, in Italy, in INAF and Scuola Normale Superiore, then the group of Fabian Walter in Max Planck in Heidelberg, George Becker in Riverside, Shawi in Arizona, Emma Ryan Weber in Swinburne, and many other people around the world. By construction, this is a multi-purpose survey. In particular, of course, we want to study the ionization process through the Lyman alpha and Lyman beta forests. And you have already heard a talk by Yongda Zhu yesterday on the dark gaps. And after me, there will be the talk by Sarah Bott, master student Sophiacampo, who are also discussing other ways to determine properties of the ionization. Then, of course, we are also studying the metal lines in the red part of the spectra. And this is a work that is an ongoing work that is led by Rebecca Davis at Swinburne University. We're going also to study the nature of the first stars and, of course, the properties of quasars themselves and their environment. And in the next slide, I will tell you a bit more about these two projects, in particular the BAL quasars also. So here the scientific aim is to find the chemical signature of massive population 3 stars at redshift 6. And to do this, we are measuring the chemical abundances of metal-poor gaseous environment, which are traced by damped Lyman alpha systems. You know these very strong systems observed in quasar spectra, which are mostly neutral, that we identified through detection of neutral oxygen in this case. So we found 15 systems at redshift larger than 4.7. Identified along 11 lines of sight. So there are, in fact, more multiple systems in some line of sight. And sorry, I forgot to say that this is a work carried out by my master student, Alessio Sodini in Pisa. And for this system, then we measure the chemical abundances. Here you see, for example, the carbon over oxygen for our sample, which is shown by the red points here, compared with the literature sample. In particular, the blue points are the sample of George Becker of 2012, and also we have a 3 measurement from the sample of Pudel et al. 2018 and 2020. So you see that let's say that the literature sample is consistent. And furthermore, we have that this gray region here is showing the average and dispersion values for the very metal poor DLAs at redshift 3 by Cook et al. So what we see is that the high redshift values are in general agreement with the redshift 3 abundance, although if we compute the average of the redshift larger than 4.7 values, this is slightly larger than the lower redshift value. Then we have also compared the abundances for the single systems with abundance prediction, in particular for peri-instability supernovae, so the supernovae that are characterizing the explosion of very massive stars. And what we find is that the abundance pattern is never consistent with a peri-instability supernova. On the other hand, for many of our systems, core collapse supernovae with parent star of population 2 and population 1 are reproducing quite well the observed abundances. So from this study, which however, I mean, is still not maybe in its final stage, but the main message I don't think will change. So from the present sample, we have that the chemical abundances at redshift 6 for these systems are in general agreement with an enrichment due to core collapse supernovae from POP2 and POP1 stars. However, what we see is that in many abundances, in fact, we see a hint of an evolution with respect to redshift 3 abundances. A couple of slides also on the BAL quasars. This is a project led by Manuela Bischetti, who is a postdoc at the INAF Observatory in Trieste. So BAL are these very, very broad troughs observed in some of the quasar spectra, and they are tracing ionized outflows that are thrown away to very high speed from the central AGN. So you see here two examples in X230 of very strong systems, and what Manuela did was to compute the fraction of the strong buzz, which is 27% in XQR30, which increases to 47% when we include the weak BALs. Then Manuela did really a tremendous job to compare our system and the fraction that we observe at high redshift with a color-matched Sloan digital sky survey sample at redshift 2-3. And what she found was that there is, in fact, an increase by a factor of 2.5 with respect to redshift 2-3. And furthermore, as you see here in these plots, also the minimum and maximum velocities of the troughs are peaking to a much larger velocity with respect to the lower redshift. So it looks like BAL quasars are more common and stronger at early epochs, and may represent a key evolutionary phase of black hole accretion at redshift 6. And so here is my summary. So XQR30 is the survey of 30 quasars between 5.8 and 6.6, so observed with shooter at the VLT. And we hope and we think that this will be really a transformational sample for the study of the ionization epoch with the quasar spectra. Of course, we are dealing with the properties of the ionization process, and you will see more in the next talks. And the two other work that are in advanced state are these studies on the signature POP3 enrichment for which there is no evidence in our systems. And if you want to stay updated with the news on XQR30, you can have a look at the web page, which is now in progress. And I'm happy to take questions now.
Thank you very much for a great talk. So people can start typing in questions in Slack. I'll give you a second. Let me just ask a question then. So for the BAL work, you said they're color matched. Are they also luminosity matched? Or whether this is a question?
Yes.
Okay.
Yeah, we can wait a few seconds for some questions. Yeah, I guess in the meantime, I can start with one. So you had that one DLA with a very high C/O shown on plot, right? Is there an explanation for that? I mean, it didn't look like any of the stellar models actually get up to those values of C/O.
Yeah, yes. So the problem here is that, of course, we don't know exactly if what we are looking at are real damped systems sub-DLA. And in this case, when we measure the carbon 2 over carbon 4, for example, silicon 2 over silicon 4, it looks like the system could need some ionization correction. So let's say that in almost all the cases where the abundances were a bit peculiar, in general, we could explain them with the fact that we should need some ionization correction.
Yeah, still no talks or no questions rather. Oh, here's one from Gabor. Regarding the increase of BALs, is there any evidence for color selection effects?
No, in fact, this is I mean, what Manuela was trying to test. So what she did was to really try to select the Sloan quasar in the same way, I mean, of course, in the rest wavelength, as the X2R30 quasar. And it looks like even if, I mean, if we don't do any color selection, in fact, the increase in fraction is even larger. But doing this color selection, still we see the factor of 2.5 more BAL in the high redshift sample. So the work of Manuela was really to try to avoid this bias due to the color selection, in fact.
Yeah, I guess if I could follow up, I mean, what does it mean physically that your BAL fraction is so much higher? I mean, does it mean you're seeing further down into towards the accretion disk in the emission or the absorption?
The quasar at this.
You're breaking up. Is that for me?
I mean, the quasar at this
Oh boy.
redshift are in a more violent.
Okay,
can you hear me?
I guess yeah.
Yeah, now.
Okay. Sorry. Yeah, no. So the possible physical. Can you hear me?
Yes.
Oh,
yeah.
Okay. Yeah, okay. So I think that the possible physical explanation is that there is this more violent maybe phase of accretion at this high redshift that is also causing these strong outflows.
Okay, great.
Okay, I think our time is up. So if you have more questions, please continue on Slack. And next we have Sarah tell us when reionization ended.
Hi, can you hear me?
Yep.
Okay.
Please.
Right. Hi, everyone, and thanks for giving me a talk at this great conference. Today, I'd like to present some new measurements at the end of reionization. We've heard quite a bit about reionization yesterday already. Reionization is a phase transition by which the hydrogen in the intergalactic medium goes from being completely neutral at high redshift to homogeneously ionized around redshift 5 and then all the way to the present day. We can probe the end stages of reionization quite conveniently by using high redshift quasars as skewers, as shown here. So the continuum emission of the quasar is absorbed by the foreground IGM. And you can see that at redshift 5 or so, there's a lot of transmission left in the last remnants of the Lyman alpha forest. But by the time we get to redshift 6, there is not much transmission left at all. Interesting things are happening in this intermediate region where we observe too much scatter between quasi-sightlines at the same redshift. This was illustrated dramatically by this pair of sightlines, the black one here showing a large amount of transmission and the red one being completely absorbed, even though they're at the same redshift range, 5.6 to 5.8. So in other words, there is an extreme contrast in optical depth of Lyman alpha, even at fixed redshift. So it has been shown that this extreme scatter in optical depth cannot be explained in a homogeneously ionized universe by accounting for density fluctuations, or even when you include temperature fluctuations. So instead, the models that can reproduce this observation involve a very late end to reionization. So where these opaque absorbed troughs actually contain gas that is 10% neutral or more, and or a short mean free path of ionizing photons inside of ionized regions. So the physics at the end stages of reionizations have been shown to have consequences for both the 21 centimeter signal, as well as the possible sources of reionization and their properties. So of course, we'd like to understand a bit better what's going on. And the specific question I wanted to answer, and we now can, thanks to the XQR30 sample, is when does this optical depth scatter end? So in other words, at what redshift does the universe fall in line with being homogeneously ionized and the phase transition is complete? So to answer this, we use the XQR30 sample that Valentina just presented, which are shown here. Because we are fighting cosmic variance, we do have to supplement it with ever so slightly inferior spectra from Extruder and ESI. But the resulting sample is still one of the largest and represents a leap in data quality by a factor 2 to 4, depending on how you want to count it. Okay, so as always, when you want to push a measurement to new levels of precision, you're going to run into a new type of systematics. So of course, the old ones we already knew, like accounting for the effect of the quasars in the background or overlap with the Lyman beta forest, the exclusion of galactic medium from the measurement, which we can now do to a very high accuracy, thanks to the metal identification in XQR30. As well as new systematics. For example, in the sample, we were very careful to only use 2 spectrographs and make sure there were no differences in data reduction or instrumentation between the 2, which we checked carefully, as well as fixing more arcane effects that were introducing covariance as fixed redshift. One systematic I'd like to spend a minute on is this issue of continuum reconstruction. So this is a quasar at redshift 2, and it's Lyman alpha forest. And as you can see at redshift 2, you can kind of guess or where the intrinsic continuum of the quasar is, just shown here in blue. But at high redshift, the Lyman alpha forest is almost completely absorbed. So instead, we have to predict or reconstruct where this continuum is based on the features that we do see. These are 2 methods that were used in the past studies to measure the Lyman alpha optical depth at high redshift. It's PCA and Paolo in purple and green. And not only they're not very accurate, but you can also see they actually introduce complicated wavelength-dependent systematic biases that were underestimated before. So in this large comparative study published earlier this year, we tested 8 state-of-the-art reconstruction methods and converged on the one of the best performance, which is a version of a modern log PCA, shown here in red. And this plot shows the residuals of our reconstructions in a low redshift test on about 5,000 EBOS quasars. And you can see there are no wavelength dependent effects in the predictions. And for the first time, we have a firm handle on what exactly the empirical uncertainty is from low redshift. And it turns out correcting this systematic made the largest difference in addition to data quality. Okay, so here are some results. This is the measurements of the mean optical depth of Lyman alpha measured in chunks of 50 co-moving megaparsecs towards our 67 sightlines. You can see that at low redshift, the distribution of measurements is even by eye roughly Gaussian, and each individual measurement is much more accurate than the distribution it's sampling, which is why we need a large number of them. By the time we get to redshift 5.6, you can see this extreme contrast between extremely transmissive and opaque sightlines, and some sightlines remain transparent even at the highest redshifts, although only a few. The evolution of the mean flux is extremely smooth. This plot shows the evolution of the mean flux in flux space. Again, you can see it's extremely linear from redshift 4.9 to 5.6, as shown in red. We are in vague, in fairly good agreement with past literature samples, and we have been able to track down almost all of these disagreements to higher data quality and the removal of this continuum reconstruction systematics. So hopefully a very nice relation for models to calibrate to. Okay, so what about the distributions at fixed redshift? These distributions in black are the new ones showing the distribution of optical depths compared to the previously state-of-the-art results in red. The data quality and the removal of systematics have had a comparable effect of making everything smoother. So you can see the black distributions have less spurious features in them. We have better exclusion of galactic material. And the removal of systematics also introduced some systematic shifts in the data before. You can also see that the fraction of non-detections is much lower, especially at redshift 5.8, because our observations are deeper now, thanks to XQR30. So actually, the number of non-detections has shrunk by a factor 3, although not at redshift 5, where most sightlines are 6, where most of them are still saturated. Okay, so now we can answer the question I asked at the beginning. When down to what redshift do we see excess scatter in the Lyman alpha optical depth distributions? So to answer this, we compared our observations divided in bins of 0.1 in redshift to homogeneous UVB models. I'm going to show results from the Nix simulation, but we also cross-checked with Sherwood. Both of them use a homogeneous Hartle-Medow UVB, and wanted to check that changing the box size or the code or the number of snapshots was not having much of an effect, as I'll show briefly at the end. All right, so for our comparison, we use a fully forward modeled maximum likelihood approach, in which for each measured optical depth tau along a sightline, we post-process the entire simulation to the optical specificities of that sightline, including any masking, wavelength sampling, flux uncertainties, and continuum uncertainties. We compare that to observations to get the probability of measuring this tau in this sightline. Then we aggregate these probabilities into a data likelihood. To interpret this likelihood, we then create 10,000 mock data sets with the same size and all observational specs as the observations. We get a distribution of simulated likelihoods, and then by comparing those, we can deduce the probability of our full data set of observations, instead of having a high-level summary statistic. These are the distribution I'm showing at the bottom. These are the distribution of simulated likelihoods in 10,000 mocks in blue, and a KDE as the blue curve. And the black line is the likelihood of the observations at redshift 5, 5.1, and 5.2. While the top panels are the observed distribution functions in black, and the 1 and 2 bootstrap uncertainties from the simulations in blue. And you can see that at these low redshifts, where our distributions are actually exactly as expected from the homogeneous UVB models, they fall within the central sigma. And this is a great sign because it means we're not missing any crucial systematics that we haven't post-processed the simulations with. So no signs of excess scatter at these low redshifts. We start to see tension at redshift 5.3, where our data has slightly too much width to it. It falls in the tail of what you would expect randomly. And then by the time we get to redshift 5.4, the observed data sets are strongly excluded by the models at our sampling limit of 4 sigma, as well as at redshift 5.5. And of course, at all redshifts above 5.5, the existence of these extremely opaque troughs has already disproven homogeneous UVB models, but you can also see that the entire distribution shape is far too broad. All right. So in summary, this plot shows the tension between the homogeneous UVB models and our observations as a function of redshift, or Sherwood and Nix as the 2 colors. And basically homogeneous UVB models fit extremely well up to redshift 5.2, which is remarkable considering that Sherwood actually fits the Lyman alpha forest all the way down to redshift 2 extremely well. And divergences from these simple homogeneous UVB models happens fairly quickly by redshift 5.4. So we have not investigated possible causes yet of this, but it is broadly consistent with a late end of reionization. Because if the last neutral patches of gas are ionized around redshift 5.6, then you would expect temperature density fluctuations to persist for a bit longer because of the different timing of reionization. But other explanations could be possible, like late persisting fluctuations in other physical parameters. All right, so in conclusion, thanks to the XQR30 sample, we have really pushed the study of the high Z Lyman alpha transmission to a new precision regime. And from the point of view of the mean Lyman alpha optical depth, the transition to a homogeneously ionized IgM is complete at redshift 5.3. Thank you.
Thank you for a great talk. So let's wait for the questions on Slack. Or waiting, let me ask a question. So what is the neutral fraction that you measured at redshift 5.3 when you said the tension sort of started?
Right, so this is the neutral fraction measurements up to redshift 5.3. It's a bit low. So at redshift 5.4 and above, we only give those as limits because the calculation of the neutral fraction relies on the model comparison. And you can't assume that the homogeneous UVB models are correct at these high redshifts. And we think that's maybe why this 5.3 point is a bit low. It's at around 3 times 10 to the minus 5.
Okay, thank you.
Yeah, so give people a couple of more minutes to ask questions, but I had sort of a question about the size of these regions. I seem to remember when George Becker I was talking to George Becker, he was talking about how these troughs actually extended for significantly larger than 100 megaparsecs, some of them. So I'm just wondering if, do you think the simulations might, even the, your large volume simulation might be missing some of these very largest troughs that might be giving rise to some of these most extreme deviations?
For sure. I mean, but even larger boxes at redshifts more than 5.5 cannot reproduce the troughs.
I see.
At low redshift, actually, our results agree very well with the ones that Youngda presented yesterday, because they don't find any troughs more than 30 megaparsecs below 5.3. They just seem to end.
Okay.
But in our measurements, we actually checked that if we exclude all troughs at redshift 5.4, we are still in strong disagreement. So this is this plot here. At redshift 5.4, we actually, our measurement doesn't depend on the existence of these troughs, because this is showing them just cut out. And it's really the variance of the measurements of the entire distribution.
We have one question from Brandt. How robust are your conclusions about the homogeneous UVB models to photoionization and photoheating history that you adopt, specifically Hartman et al. 2012? Can simulations with other photoionization or photoheating histories explain your data?
At 5.6, they can't, because we already know this from the long troughs comparisons. We haven't checked if at redshift 5.4, just changing the slope of the temperature density relation would make a difference, but we suspect it will not. You have to have scatter between individual locations, and not just an adjustment of the whole.
Thanks.
All right, I think we should move to the next talk. So thank you, Sarah, again. Next, we have Sophia talk about new upper limit of neutral fraction. Please go ahead.
Oh, sorry. Okay. Hi, everyone. Thank you for this amazing opportunity. I am Sophiacampo, a master's student from the University of Pisa, and today I will talk about my work thesis on new limits on the neutral hydrogen fraction at redshift around 6 using quasar absorption spectra. This work was done in collaboration with Professor Valentina Doderigo and Professor Messinger, and with the XQR30 team. About the reionization, we know that it is expected to happen at redshift around 7, 8, and it is a complex and highly inhomogeneous process. So modeling ionization is a significant challenge. Quasar absorption spectra are a powerful tool to study this process, because they are one of the main probes of the ionization epoch. From the detection of the flux in the Lyman alpha forest in the quasar absorption spectra at redshift lower than 6, we know that the universe is highly ionized, while at redshift higher than 5, the Lyman alpha forest becomes opaque due to regions with trace amount of neutral hydrogen inside the ionized intergalactic medium, with a neutral hydrogen fraction between 10 to the minus 5 or 10 to the minus 4, or due to neutral patches pre-overlap with a neutral hydrogen fraction around 0.1 to 1. So the main goal of this work is to derive updated and more stringent limits on the neutral hydrogen fraction using the new sample of intermediate resolution high signal to noise ratio quasar spectra at redshift between 5.8 and 6.6, which is of course XQR30. The limits are computed using the model-independent method of the dark pixel fraction, which was developed in Messinger in 2010, and then implemented in Megier et al. In 2011 and 2015. We focus our work on the Lyman alpha and Lyman beta transition, because even trace amounts of neutral hydrogen in the intervening intergalactic medium along the line of sight will suppress the observed flux due to the strong absorption cross-section of the Lyman alpha and Lyman beta transition. So any remaining neutral patches along the line of sight to distant quasar will generate in the spectra dark pixels. Here there is an example of a quasar high redshift quasar absorption spectra from Becker et al. In a paper of 2015, which illustrates the key spectral features used to infer intergalactic medium properties approaching the epoch of ionization. About the method that we used in our study, we used the dark pixel fraction method, which is the least model-dependent constraint on the neutral hydrogen fraction. It is, of course, an upper limit of the neutral hydrogen fraction because we cannot differentiate the causes that made the Lyman alpha and Lyman beta forest opaque. We used two criteria to define a dark pixel. With the threshold method, we define a dark pixel using the flux and the noise properties of the spectra. In fact, a pixel is dark if its flux is less than n times its measured noise, where n is an arbitrary threshold value. In our case, we adopted an n equal to threshold values. While with the negative flux method, if the noise in the extracted spectrum is symmetric about zero, pixels that intrinsically have zero flux will have the equal probabilities to be scattered into positive and negative values. So we estimate the number of dark pixel counting pixel with a negative flux and then multiplying by a factor of 2 for the Lyman alpha and Lyman beta forests. While in the case of the combined dark fraction, from redshift overlapping with the Lyman alpha and Lyman beta forest, we multiply our count by a factor of 4. Again, because a pixel with zero flux will have 1/4 chance in this case of having observed negative flux in both the Lyman alpha and Lyman beta forest. To compute this limit for the preliminary results on the neutral hydrogen fraction, we use both the dark pixel fraction method just explained. We adopted an n equal to threshold for the definition of a dark pixel in the threshold method. We use the spectra Rabin to 50 km/s, which is the gene scale of the ionized intergalactic medium at mean density, which provides a natural quantization scale for the density field. The original pixel size of the spectra is 10 km/s. Finally, we divided the redshift range in step of 0.2 width. Here there is an example of a quasar absorption spectra used in our sample, a quasar with an emission redshift of 5.85 Rabin to 50 km/s, zoomed in our area of interest. What we obtained, so some results. The left panel shows the constraint derived from the pixel with the negative flux, while the right one shows the results derived by counting dark pixel using a 2 sigma flux threshold, while the upper panel above both the plots illustrates the number of independent line of sight contributing to each redshift pin. About the error, we use a jackknife statistic to derive the mean and the variance from the fraction. As you can see from both the plots, the evolution of the neutral hydrogen fraction shows an almost constant behavior down to redshift 5.7, and then it starts decreasing toward redshift around 5.3. And then it keeps again constant until the lower redshift we could study, which is 4.7. The two methods yield comparable results, which are consistent with the error, although the negative flux method results in lower dark fraction. This could be due to many pixels with small positive flux contributing to the flux threshold method. In fact, by pushing the threshold to negative fluxes, many pixels are eliminated in the count for the negative flux method. Finally, we compared our results with those estimating Megier et al. In a paper of 2015. To compare these results, we estimate the neutral hydrogen fraction using a pixel, spectra ranging to 300 km per second, which is consistent with a 3.3 moving megaparsec pixel size used in the paper of Meguiar et al. Here there are our results compared with those of Meguiar. Those results are related to the combined Lyman alpha and Lyman beta forest because it is a more stringent limits, because in this case we require that the overlapping pixel in both forests are dark. As you can see, our results are slightly higher than those of Meguiar, but they are consistent within 3 sigma. This could be due to the fact that we have a factor higher than 2 line of sights with respect to the results in Meguiar et al. In conclusion, we have a great improvement for the previous upper limits by extending the redshift range to redshift about 6.5, by increasing the number of high quality line of sight by a factor of 3 or more. And finally, we provide a less stringent results than before, which is in better agreement with the recent models, which provide higher values for the neutral hydrogen fraction, as you can see in the right panel, which shows the evolution of the neutral hydrogen fraction estimated by Quinn et al. In a recent paper of 2021. Thank you.
All right, thank you very much. Let's wait for people to ask their questions on Slack. Can you go back to the comparison with Meguiar plot? I think that's probably the one that people want to stare at. So do you have, before, I don't see any question yet, so let me ask a question first.
I don't see any questions.
Yeah, let me ask a question first, sorry.
Yes.
What is the sort of the difference in the signal noise limit from Meguiar's sample to the SQR30? I mean, the SQR30 must have higher signal noise in general, right? Which means sigma is lower.
Yes. I think you mean our results in comparison with those in Meguiar.
Yeah. Mm-hmm.
Yeah. About the error.
Yeah. Yeah. What is the sigma in Meguiar compared to the sigma in your sample?
I don't remember the error. These are upper limit related with already 1 sigma in this value.
Yeah. So I'm just wondering if you degrade your data to the Meguiar data, whether you recover the result or not, because your sigma is lower, so your dark pixel fraction will be lower as well, I guess.
Yes.
So if you degrade your data, whether you can explain this discrepancy. That's maybe an easy test to try.
I don't know. Maybe the fact that we have higher number of line of sight, which gives a different error. It's a good question. Yeah. I don't know.
Yeah.
Maybe I will think about it. Yes.
Stefano Cristiani has a question. How sensitive are your measurements with respect to systematics in the 0 level flux of your spectra?
About 0.1. It's the error related to our results in this redshift.
It's plus or minus 0.1 roughly.
Yes, plus or minus 0.1.
Okay, great. Tom Toons has a question. In the one spectrum you showed, I had the impression there were fewer transmission excursions to positive transmission and more excursions to negative transmission in the dark gaps. Did one of your plots examine this?
Yes, here. I can hear so well. So can you repeat the question, please?
Sorry. In the
Let me read it. In the one spectrum you showed, I had an impression there were fewer transmission excursions to the positive transmission and more to the negative in the dark gaps. Did one of your plots examine this? I think he's referring to the one that you showed the dark gap. So let me do the next plot.
Yes, here. So the question is about the neutral hydrogen fraction. I don't understand, sorry.
Yeah, I'm not sure either. So maybe you could continue that discussion.
Yes, yes. I will answer in the Slack channel.
Yeah.
Yes.
Okay, if there's no more questions on Slack,
yes,
then we'll,
thank you.
Yeah, thank you again, and we'll move on to the next talk, which will be by King-Yi Lu on constraining ionization history from quasars in the Subaru survey of low redshift high-redshift quasars, low luminosity high-redshift quasars. I'm sorry. Go ahead, please.
Yeah, okay. So hello everyone. My name is King-Yi Lu, and I'm a master student at National Tsinghua University, work with Professor Tomo Goto. And today I'll talk about our constraint on ionization history using the red frame UV spectra of the shocks, using the reference spectra of the shocks quasars. And as mentioned by previous speakers, quasars are very powerful probe of the ionization. Basically, we can use we can measure the redshifted lemma of absorption in their spectrum. And if you have many quasars, it is possible for us to constrain the dispersion of optical depths in some certain redshifts. So it's quite important to have a large sample of quasars. And another quite common way to measure the ionization with quasar spectra are measuring the H2 bubble size, which is also called the near zone size or the proximity zone size. And the proximity zone is basically the distance from quasars to where the quasar radiation equals the background one. But observationally, we used to measure it by measuring the distance from quasars to where the transmission first dropped down to 0.1. And using this way, we can have less assumptions. But as shown in this equation here, the size measured using this definition actually have an additional term, which depends on the lemma of optical depths. And also in some recent work, it has been found that the near zone size actually scales with quasar lifetime at around 5.5 to seconds. Anyway, I will show the result of the near zone size of this work later. And in addition to this, we also try to constrain the background photon incidence rates using these definitions with the method in these calculus papers. Basically, we assume a background lemma for its output depth as high redshift, and also some certain flux dropper profile of quasars around its near zones. And we measure it by fitting the transmission profiles in near zones using different background photon incidence rates. And The sample in this work is from the Subaru Heisey exploration of low luminosity quasar projects. Basically, because of the deeper surface depths of the HSC, we are able to recover pentaquasars in the surface area. So here I show the redshift and the UV magnitude of the Schultz quasars and other known quasars. And the Schultz quasars are in principle two magnitudes fainter than others brighter one. And also the sample size is around, you can see that the Schultz population is almost half of the known quasar population at redshift above 6. So we can try to use this to tighten the constraint on realizations. And also know that pentaquasars are more common in the universe. So we can use them to probably more common IgM environments around them, around the quasars. And the Schultz is an ongoing project. So far, there's around 93 quasars identified by in the 900 degrees square of the sky. And after quasar selection, we have some spectroscopy follow-up and also the near-infrared follow-up and the ALMA ones to determine some black hole properties. But in the work here, we will only use the quasars, we'll only use the spectra from the first spectroscopy follow-up. And these quasars have very low spectral resolution and very low SNR. So we cannot really use this to measure things such as transmission spike or dark pixels. And also, most of the quasars in this work, the redshift is determined by the Lambda alpha emission lines. So our sample suffers from quite a large uncertainty of redshifts. So we will try to look at our results only statistically. And for the continuum of these quasars, we adopt the power law continuum plus some emission line Gaussian fitting, like the Lambda alpha emission lines and the nitrogen ones for these quasars, because this always works better than the PCA on our current data. And here I show the mean IgM opacity measured using the Schultz quasars. This panel is just the spectral coverage of the Schultz quasars. Each horizontal lines here is one quasars. And we try to measure the transmission in these gray bands. They are at reference longer than lambda beta emission, but shorter than the quasar near zones. And the gray dots here are the transmission value in these gray bands. And red dot here is the mean line of sight transmissions in these orange bands. So we can see that the transmission dropped to 0 at around redshift 6, which is consistent with others' work. This is around the tail end of realization. And also we try to convert it to the upload depths. But as you can see here, at higher redshift, we can't really tell whether the upload depth is going up or not because of our limited detection limit for the upload depths. And here I show our quasar near zone size measurements. The red shaded region is the median value of the Schultz quasars near zone size. And we try to fit their evolutions at redshift, just evolution here, the red line here. And we found it steeper than the work done by others et al., but shallower than the one in earliest work. And we think this may be due to the transmission spike at slow redshift, and also actually the sky residues in the spectrum. Because we also try to fit the evolution using only a quasar with redshift higher than 6. And the trend is showing here, the red dotted line. And yeah, it's almost flat. So it shows that the evolution of near zone size, it can probably not tell us things about the realization's history. And also try to compare the near zone size with the size in simulation. The magenta one, and the orange lines here from Davis and Chet's work. And we found the median neutron size of the Stokes quasars consistent with the quasars of lifetime around 1 to 100 mega years at redshift lower than 6.5. And at high redshift, its size is smaller than 1 mega years. But we still need to obtain more higher quality near-infrared spectra to confirm this trend. And here I show the background photon rates evolutions using the method I mentioned previously. And it's probably a bit ambitious to do this because of our data quality and many assumptions made in this method. But I think it's still interesting. It's still important to push the constraint of the background photon rate to redshift higher than 6. Because as you can see here, this from these gray lines to black lines, our models assume different things such as different ionizing photon escape fraction or different reionization redshift. And also this bond is mostly contributes from quasars. And the second one here is mostly comes from radiation of high redshift galaxies. So if we can map the shape of the evolution at high redshifts, it is possible for us to rule out some model of realizations. And the red dots here are the median value of this individual measurement of the shape quasars. Basically, what we can say from here is that we cannot really tell which model here is correct, but at least we can say that our measurement is consistent with the model using Fancy-Stockholm galaxy-driven realizations. And I will leave my summary slide here. Thank you very much.
All right, thank you for a great talk. We'll wait for questions on Slack. So there's one already.
It says, not sure if the uncertainty is too large here, but can this sample be used to do similar forest opacity fluctuation measurements as Sarah Bossman presented, or the dark fraction upper limit that Sophiacampo just showed?
Not really. We try to measure the dispersion of optical depths using these samples. I have a slide showing here, but as you can see that we seem to see some evolution in this dispersion of optical depths, but it's actually due to the distribution of detection limits of all spectra, not really due to reionization effects. And if you compare it to Boltzmann's work, you can find that we cannot really push the limit of optical depth to higher ones.
Great. And Tom Toons asks, is the data also consistent with a model in which brighter galaxies dominate the emissivity?
Actually, we didn't compare that to those models, so we cannot answer this. But yeah, we will try to answer this on Slack.
Any other questions?
Well, let me ask a question, then I'll wait for others. Did you find any very young quasars as Ehlers or those sort of small proximity zone size quasars in your sample, for the ones that you have good redshift measurements at least?
For those, I think it's better to check the work done by Ismoto-sans. Actually, she presented the results last year. She used the only near-infrared spectra which have higher SNR, and only with redshift determined by other lines, beta lines. And she did find some quasars with very small neutron size. Yeah, so there is young quasars in the Shook's sample, but we can't really tell it from the current data set.
Thank you.
And just to be clear, all of these near zone sizes are assumed to be spherical or near zones, or do you account for any potential variation due to the fact that the quasars might ionize one direction versus another?
I think this because it is just observational one, so we don't really try to check the potential things.
Okay.
Okay, so I think people have, if you have more questions, can continue for the discussion on Slack, and we're told to not start early, so let's just transition to the next talk first, and that we'll wait for a minute before we start. So Wade, can you share the screen? All right.
So can you see my screen?
We're seeing the Slack, not the slide. Okay, now it's good.
Okay, so hello everyone. I'm Wade Hu. I'm a graduate student from University of Science and Technology of China. I'm working with Junxian Wang from USTC on the epoch of realization. I would like thanks to the organizer for this opportunity to present our recent work here. The title of my talk is Lemma Alpha Protocluster Redshift 7. This is the outline of my talk. First, I will introduce a little background about the realization and the Lagos survey, and second, I will present the discovery of a protocluster Redshift 7 and its properties, and last I will summarize my talk. So Galaxy clusters are the largest structure in the universe and has been extensively used to constrain the cosmological parameters and to investigate the galaxy evolution in mature environments. However, the formation of the cluster is not well understood, so it is essential to investigate them when they were young. That is in a protocluster stage. Numerical simulations have predicted the protoclusters can significantly contribute to the cosmic star formation rate density with fraction up to 30 to 50% at redshift 6 to redshift 10. So they can provide a significant fraction of ionizing photons and may be crucial in driving the timing and topology of the realization. Previous talks have shown that the quasar could be an excellent probe of the epoch of realization. Lemma alpha emitter galaxies can also be a powerful probe when the Lemma alpha photon emitted by the galaxies passes through the intergalactic medium. It will be resonant scattered by the intergalactic medium, and the observed spectrum can reveal some properties of the intergalactic medium. For example, we can study the line profile or the line luminosity, the observed line luminosity to determine the neutral hydrogen fraction of the intergalactic medium. So we carry out a narrowband imaging survey to search for NAM alpha galaxies in the epoch of realization. The survey is named NAM alpha, is named the Nagel survey. We designed a narrowband filter to search for NAM alpha emitters at redshift 7. We optimally designed the filter to avoid the strong sky emission lines and atmospheric absorption. We can use this filter to search for NAM alpha galaxies in the redshift range of 6.89 to 6.97. The narrowband filter was installed on the dark energy camera on a Blanco 4-meter telescope. The dark energy camera has a very large field of view and a red sensitive camera. Its total response at about 19,600 angstrom is still larger than 15%. So this combination makes the Nagel survey one of the most efficient survey in searching for NAM alpha emitters in the epoch of realization. We aim to construct a unique narrowband selected NAM alpha emitter sample at redshift 7. We expect to select more than 600 NAM alpha emitters. The area coverage of the Nagel survey is very large, larger than 20 square degree. So it is the largest narrowband imaging survey for galaxies at redshift 7 and above. We adopt a wedding cake strategy to search for both bright and faint NAM alpha galaxies. Based on this NAM alpha emitter sample, we can study the galaxy the properties of the galaxies in the early universe and the history of the realization. So up to now, we have observed 4 fields: the cosmos, change-relevant field south, gamma, and the wide field. We have selected 174 NAM alpha emitters at redshift 7, and the recent results show that the neutral hydrogen fraction at redshift 7 is about is lower than 0.33. So the protocluster region was firstly shown some interesting signal in 2017. In 2017, we selected 23 NAM alpha emitters based on 34 overall narrowband exposure in the cosmos field. Here I show the spatial distribution of 23 NAM alpha emitter candidates. The size of the circle indicates the NAM alpha luminosity. If we focus on the bright NAM alpha emitters with luminosity larger than 10 to 43.3, you can find the 1 and 3 is very close with the distance is only 3.6 arc minute. The bottom shows the pseudo color cutout of this 2 NAM alpha emitter, where the narrowband is green. Sorry, narrowband is green, the Z band blue, and Y band red. So you can find they are very green and compact. These 2 NAM alpha galaxies were subsequently confirmed by the Magellan spectroscopic observation. Their high signal to noise ratio spectra shows significant, highly asymmetric line profile. So finding 2 such bright NAM alpha emitter galaxies in very close distance is very encouraging. So we decided to take more narrowband observation on this field to figure out the physical nature of these 2 NAM alpha emitter. In 2019, we obtained 47 over narrowband exposure on the cosmos field and selected 49 9-alpha emitter galaxies. So this plot shows the spatial distribution of 9-alpha emitter candidates, and the contour shows the galaxy number density. You can see a highly overdense region consists of 40 9-alpha emitters. It is identified as a protocluster redshift 7 with overdensity of 5.1. This is the two-mean spatial distribution. We carry out spectroscopic observation for using Magellan telescope, and for 40 9-alpha emitters from WHO 2019, 11 was spectroscopically confirmed. The volume of this protocluster is 66 times 30 times 26. The overdensity is 5.1. Here shows some spectra of 9-alpha emitters. So based on its overdensity, we derived its present day mass to be 3.7 times 10 to 50 solar masses. We use several methods to find as much 9-alpha emitters of the protocluster as we can. Firstly, we 4 lower grade 9-alpha emitters were identified by the spectroscopic observation. Secondly, we noted that the transmission curve of narrowband overlaps. The transmission curve of a narrowband overlaps with the HIC narrowband, so we stacked the 2 narrowband images and selected 3 more faint 9-alpha emitters. In total, we discovered 21 member 9-alpha emitters, and 16 have been spectroscopically confirmed. So the 9-alpha galaxies, the galaxy in the epoch of realization can produce a large amount of ionizing photon and ionize its surrounding neutral hydrogen. So the ionized bubble can grow and merge with the adjacent bubble and into a very large ionized bubble. The protocluster can, in the epoch of realization, can lead the production of such ionized bubble because its high number density of galaxies. We calculated the bubble size of the member galaxies of the protocluster based on relation between 9-alpha luminosity and the bubble size. We found the total volume of ionized bubble is slightly larger than the volume of the protocluster. This demonstrates individual bubbles has overlapped, and the bubble are in the act of merging into 1 or 2 giant bubbles. The intergalactic medium within the protocluster is almost fully ionized. So for this protocluster, we have submitted a proposal to James Webb Space Telescope to observe with low spec, and we got 35 hours. We are going to observe O2, O3, H alpha, and H beta lines of the member galaxy of this substructure. Please stay tuned for the JLabST results. So I leave a summary here, and if you are interested in larger survey, you can scan this QR code for the publications. And so thanks for your listening. I stop here and take questions.
All right, thank you very much for a great talk. Let's wait for questions on Slack. While we're waiting for questions, can you tell us more about the JWST program? What are you observing? How many galaxies and so on?
So we are observing the galaxies in this substructure. There are 8 galaxies, and we will observe O2, O3, and H beta and H alpha emission lines to investigate their ISM properties, the Lyman continuum escaping mechanism, and so on.
Yeah, we have a question from Yusheng Qin. Can you elaborate a bit on the estimation, on how you estimate the bubble size?
How to estimate bubble size? So we estimate bubble size based on this relation between the Lima alpha luminosity and the bubble, the radius of the bubble, and we derive the bubble of every member galaxies in this protocluster, and we summed the simply summed the bubble, the volume of the bubble.
I guess the question is that requires knowing some ratio between the continuum or the ionizing flux and the Lyman alpha luminosity. Do you have to make some assumptions about that?
No. So this simulation calculate the bubble base. Yeah, this simulation calculated the bubble size based on
Okay.
the
Using that
star formation history and derived the galaxy, the current galaxy, the galaxy Lima alpha luminosity and the bubble at a different redshift.
Yeah,
we
another
didn't
quick
use
question.
the.
Oh, sorry, go ahead.
Okay. Oh, go ahead, please.
Just quick question. Yisheng said I probably missed it, but what's the UV magnitude of these galaxies?
What magnitude?
UV magnitude. So do you have continuum measurements?
Some of them were detected in the Y band or J band, so we can derive their UV magnitude based on those near infrared photometry.
Okay. Well, maybe you can give more, discuss more. And Tom Toons asked a question that the observed average density could differ from the actual average density of Lyman alpha emitters if many Lyman alpha emitters are invisible because they're in regions that are too neutral. Would this affect your density estimate?
Yeah, indeed, the overdense region could contain more neutral hydrogen and thus a severe attenuation by the neutral hydrogen. On the other hand, the overdense region could have much higher star formation rate, so boost their Lima alpha luminosity. These two effects could cancel each other. So, however, we don't know which effect will dominate the result, the observed overdensity of the Lima alpha emitter.
Great.
So I cannot tell the.
Okay, thanks again for a great talk. Let's move on to the final talk of this, this session. Thank you. So been In Taizhong talking about boosted Lima alpha transmission of IgM in UV bright galaxies. Please go ahead and share the screen. All right.
Hello, do you see my screen?
Yeah, please, go ahead.
Yeah. Yeah, hi everyone. I am In Taizhong, a postdoctoral fellow at NASA Goddard. Today, I'm going to talk about boosted Lyman alpha transmission of the intergalactic medium in UV bright galaxies. In the previous sessions in this SAZERAC conference, there were lots of great talks already on Lyman alpha during the epoch of reionization. Then here, I'm presenting my work also on Lyman alpha during the epoch of reionization, but more focused on its inhomogeneity and galaxy UV magnitude dependent Lyman alpha transmission in intergalactic medium. So for this work, I'm work with the clear collaboration team with the listed core members here. And there were numerous talks on Lyman alpha, so I'm not going to give too much of an introduction, but briefly remind you. So the Lyman alpha is sensitive to the amount of neutral hydrogen. So the evolution of Lyman alpha visibility has been used to trace the evolution of neutral hydrogen of the IgM during the epoch of reionization. Particularly, I'm here more focusing on the distribution of Lyman alpha equivalent width in my previous Lyman alpha studies on the right panel. As this analysis of Lyman alpha equivalent width uses more observables than the Lyman alpha fraction, such as Lyman alpha flux and the galaxy UV magnitude. The Lyman alpha equivalent width distribution is often described in exponentially decaying functional form with the characteristic e-folding scale W naught here. So the characteristic value of W naught represents the Lyman alpha strength statistically. So in short, in the bottom figure, I'm showing the evolution of equivalent width distribution from my previous study, which also suggests reduced Lyman alpha equivalent width during the Pavlov reionization at redshift of 6. However, the recent Lyman alpha studies suggest a very complicated picture of reionization. So, for example, on the right left panel, I'm showing the neutral fraction measurements of the integrating medium from various works. The focusing here at redshifts 7 to 8, these Lyman alpha studies, including the measurements from my recent publication, show disagreement between their measurements. Furthermore, a set of quasars Lyman alpha damping ring analysis provided a large scale of IgM neutral fraction at redshift above 7 from their quasar observations. Such a disagreement between the IgM neutral fraction measurements directly suggests the IgM did not occur spatially uniformly, but in an inhomogeneous way. So in the same context, the various observational studies of Lyman alpha emission have provided an increasing body of evidence for inhomogeneous reionization caused by individual or groups of bright galaxies in the middle phase of reionization. So for instance, the recent findings of clusters Lyman alpha emitters at redshift 7.7 from Tilby et al., and also protocluster structure of Lyman alpha emitters at redshift around 7, just presented by Wei Hu. Additionally, a highly ionized structure with 4 clustered Lyman alpha emitters at redshift around 7.5 from my recent study suggests enhanced Lyman alpha visibility from these bright galaxies. So, and beside these studies, we have noticed numerous other studies presented in this conference provide increasing body of evidence of ionizing bubble structures from Lyman alpha observations, particularly from bright galaxies. All of these suggest on accelerated reionization nearby these clustered brightest galaxies. Being motivated by these recent findings, we attempt to conduct statistical analysis of Lyman alpha equivalent width distribution, which is dependent on galaxy UV brightness. So in order to do that, we utilize a spectroscopic data set of HST slitless Gaussian survey called CLEAR. The CLEAR is the Candles Lyman alpha emission at reionization experiment is the cycle 23 HST observing program. The PI is Akesh Popovich at Texas A&M, and the CLEAR observes the 12 fields in Candles Goose field, as shown in these figures, to 10 to 12 orbit depths with the G102 Gaussian and the HST WFC3 camera. So in short, we extract the CLEAR Gaussian spectra of around 100 redshift 6 to 8 candidate galaxies from this data set. So the photometric galaxy selection is based on the Finkelstein et al. 2015, and the spectral extraction was done with Grizzly. And we thoroughly performed the inspection on emission line and continuum detection candidate. But unfortunately, we do not find any of these new detections from CLEAR. So lastly, we cleaned out contamination sources carefully based on the multiple PA position angle observation data. This resulted in HST Gaussian spectra of around 100 redshift 6 to 8 candidate galaxies. Those are non-detections though. The CLEAR provide a wide dynamic range of galaxy UV magnitude compared to other targeted ground-based observations that is blind, because it is blind survey. However, what it can do with non-detection only is just providing upper limit of the Lyman alpha equilibrium distribution. So we thought better combine these clear data set to the existing deep CAC observations. So those are denoted as the cyan and yellow rectangles here, which are DEMOS and MOSPHY observation pointings in the GOOS field, and that are published in my previous papers. And those CAC data set provide the spectroscopic data set of additional 100 redshift to 6 to 8 candidate galaxies with 13 spectroscopically confirmed Lyman alpha emitters. As a result, we comprised HST plus CAC data set of over 200 redshift to 6 to 8 candidate galaxies in order to explore the MUV dependency of Lyman alpha equivalent distribution and the Lyman alpha IgM transmission at redshift of 6. In the left panel, it shows the MUV distribution of sample galaxies in clear as a function of redshifts with CAC targets and M star MUV relation shown in the right panel. So all clear targets are shown open circles, and the CAC targets are shown the field blue and red circles. The wide dynamic range of UV magnitude from clear sample apparently shows unbiased nature of the blind survey compared to the targeted CAC observations, including UV faint sources. And I'm going to touch a bit of details how I can constrain the Lyman alpha equivalent distribution with a tinish number of Lyman alpha detections with a bunch of non-detections. So we introduced the methodology for constraining distribution by simulating the expected number of detections, which considers data incompleteness of observations. First, photometric redshift uncertainties and galaxy UV continuum level, and also observing conditions. Briefly, with the simulated Lyman alpha emission lines per individual targets, we assess the likelihood of detecting Lyman alpha emission lines as a function of their detected signal to noise levels. And we fit the simulated template to our actually detected Lyman alpha lines. So the red lines are actually detected Lyman alpha lines from our observation. So this is for finding the best fit evolving scale, which is reproduce the detected Lyman alpha lines. The strong advantage of this method is that in addition to our positive detection of Lyman alpha emission lines, our non-detections are highly constraining as well in the simulation step. So we applied this methodology to our clear data set as well. So here I'm going to show how much we can be benefited from including non-detections in this analysis. So in the top left, I'm showing the Lyman alpha detection limit in terms of Lyman alpha flux and rest to equivalent width that are measured from individual clear spectra. And on the right panel, the figure shows a simulation exercise on how the measurement of evolving scale would be changed with including additional non-detections. So x-axis shows the multiplied number of non-detections to the original data set. So if you have non-detections, which is doubled, that are third data point here from the original, the first data points, the constrained evolving scale is reduced and constrained with smaller error bars. So, and at the bottom, I'm showing the actual update with additional clear data set with existing CAC data set. The bottom left shows the result from my previous publication, which is based on the CAC MOSPHY data only. The data point at 6.5, that is from DEMOS dataset, and 7.6 from MOSPHY data. And now, including 100 non-detections from clear, update these measurements, as shown the purple data point here, that are slightly reduced and with smaller uncertainties. Now here I'm showing a key result of this study. So there are about Lyman alpha equivalent with distribution and the IgM transmission depending on UV magnitudes. So in my previous paper, Zhang et al. 2020, we already attempted to measure this with CAC MOSPHY data only. So as shown in this top left table, this hints at the slightly enhanced equivalent width distribution from the UV brightest galaxies compared to the fainter bin. However, the measurement uncertainties are dominating the difference. Now, the clear data set, also including the KEGDMOS data set, we comprise the spectroscopic data set more than 200 galaxies at redshift of 6. So this allows us to constrain these quantities at higher confidence level. So in the table here, I'm showing the e-folding scale measured at different UV magnitude galaxy groups and also displayed in the right panel. So y-axis is the e-folding scale of the equivalent distribution, and x-axis is the galaxy UV magnitude. And black points are the low redshift measurement from Santos et al. And our measurements at redshift of 6 are shown as red dots. The highlight is that we see a marked enhancement from the brightest object compared to the faint object, so which is unlikely from the low redshift measurements. Finally, we estimate the Lyman alpha transmission in the IGM at redshift of 6 based on these equivalent width measurements. So we define the relative IGM transmission, which is the observed equivalent width divided by the intrinsic equivalent width. As we do not know the intrinsic value, so we take equivalent width measurement from redshift below 6, where reionization nearly completed as the intrinsic properties. From this estimate, we can see that the transmission value are shown in the last column in this table. So you can see here the boosted IGM transmission to IGM from the brightest galaxies compared to the faint objects. So this indicates an inhomogeneous process of reionization with highly ionized IGM around the UV bright galaxies. And this is my summary, and I will take questions.
All right, thank you. So we'll have time for maybe a couple of quick questions if people want to put on Slack.
There's a question from Christopher. Is it possible to derive a statistical value of the Lyman alpha escape fraction from the equivalent with e-folding?
It is ideally possible, I think. So you can estimate the Lyman alpha photon production from the star formation rate from the entire galaxies. And we can derive the observed Lyman alpha light from the observation. So I haven't tried that, but yeah, I think it's technically possible, and yeah, that'll be interesting.
All right.
Yeah, we're probably out of time at this point.
Yeah, if there's no more questions, so we can continue other discussions on Slack, and let's thank all the speakers for this session. I guess we're reconvening in 45 minutes, right?